let's talk about upper and lower sums. Suppose I have a curve, and I'm not sure how to find the area exactly, but suppose I wanted to give it a pretty good approximation by dividing this into n subintervals. All right, so I'm going to take and divide it into n subintervals. All right, now for simplicity's sake, I'm going to let delta x equal b minus a divided by n. It's nice, it's regular. And I'm going to define x of I so that a is equal to x naught and b is equal to x of n. Now look what happens. If I let a equal x naught, that can be written as what? Well, let's put it in terms of delta x here. This becomes a plus, now we're going to start right here, so how many delta x's have we added? We've added 0 delta x's. And then our next one will be a plus 1 delta x. And then our next one will be a plus 2 delta x. And then our next one, let me erase that, that's kind of yuck there. And then our next one will be a plus delta 3x. Okay, you kind of have the idea. Until we reach the very end. And b is a plus n times delta x. And this is b. So we start at a, we end at b. We start at x naught, x1, x2, all right, x3, and we end up with x of n. Now this is just a way of describing our partitions. Now you see, if we take any particular delta x, we can inscribe a rectangle, all right? And if we allow, we know by the, by the extreme value theorem, golly, this happens when you do too much calculus in a day. For the extreme value theorem, I know there's a maximum and I know there's a minimum. All right, so let's let our inscribed triangle have a rectangle have a height of f m sub I, where this is a lowercase m, and let's let our circumscribed rectangle be f big M. So we are going to define a lower sum, all right, equal to, and this is going to be s, and we're going to use a little n here, a little s, a little n. We're going to find that to be the sum from I equals 1 to n of f m sub I times delta x, because the width is delta x and the height is f m sub I. And then let's define our upper sum to be big S sub n, which is a sum I equals 1 to n f, you got it, big M sub I, times delta x. Now, you can see that S little n is always going to be less than, could be equal to, S big S of n. All right. What if we try one of these? Well, let's look at this first. We can see that this area is always going to be less than or equal to the area of the actual curve, if somehow we could not have to break in these tiny partitions anymore. And that is always going to be less than or equal to the area of the circumscribed rectangles, because you're always going to have a little bit left out on the inscribed rectangles, and you're going to always have a little bit on the outside of the circumscribed rectangles, because you remember we are always picking the maximum value of the function to define your rectangles. All right, let's just try an example. Suppose I want the upper and lower sums for a region bounded by f is x squared, the x-axis, x equals 0, and x equals 2. All right, the first thing you always want to do is always go and find what your delta x is. Delta x, remember, we're going to define it to be b minus a divided by n. And yes, I want you to write this down. Now, we've given our limits from 0 to 2, so this is going to be 2 divided by n. Now, let's look at our left endpoints. Okay, our left endpoint, as we divide this into rectangles, will look something like that. So, our m sub I here is going to be 0, because that's what we're starting with, plus I minus 1 times my height, which is 2 over n. So, my lower sum, since this is always going to be inscribed here, my s, little n, is going to equal the summation I equals 1 to n of f, little m sub I, delta x. So this is the summation I equals 1 to n of f. Now, f m sub I is going to be f times 2 I minus 1 divided by n. So this is f evaluated at 2 over n times I minus 1. It doesn't matter what order you put these in here. Times delta x, and delta x in this case is 2 over n. Alright, so now is the time to do a little rewriting. This is summation I equals 1 to n, 2 divided by n. Did I forget something? Oh yes, this is, almost, hold on. F evaluated at the point is x squared. So this is 2 I minus 1 over n. Now this is going to be this whole thing squared. Don't skip steps. I do it all the time. That's not good for me. Alright, now let me factor things out. This is going to be 2 times 2 is 4 times 2 is 8. So this is a summation I equals 1 to n of 8. Let's say n squared times 1, so this is going to be n cubed, times, and now I've just got a quadratic, I squared minus 2i plus 1. Well, now we can just do our sums. So this is the summation, I equals 1 to n of 8 over n cubed, times, tell you what, let me put my summation, nope, should have left it, don't get ahead of yourself. Alright, I'm going to take and distribute this n across all of these i's. You know what, I was right. Alright, so this is times the summation I equals 1 to n of I squared minus 2 times the summation I equals 1 to n of I plus the summation I equals 1 to n of 1. Now remember I told you you're going to have to use all those. So this becomes 8 over n cubed. Summation of I squared is n times n plus 1, 2n plus 1, all over 6, which brackets, minus 2, the summation of I is n plus 1 divided by 2. Alright, plus n. Alright, so when I multiply all this mess out, I'm running out of room, so let me just give you the answer here. This becomes 8/3 minus 4 divided by n plus 4/3 n squared. Now, we're going to cheat a little bit. Look at what happens if you take the limit as n goes to infinity. Do you see what this becomes? It becomes 8/3. Now I'm going to come over here and I'm going to do this for the right endpoint because I wanted both upper and lower bounds. So for the right endpoint, the only real different thing is what m is. So I'm going to come over here and now I'm going to show you what happens when we do this right here. This is what's going to happen when I use the right endpoint. M sub I then is going to be 0 plus I, so it's just going to be your I value times the height, which is 2 over n. or times my interval level, not my height. Sorry about that. I think I said that over here too. This is your delta x. All right, so when I do my S, capital SN, this is the summation I equals 1 to n of f of big M sub I times delta x. So this is the summation I equals 1 to n. Now f of big Mi is f evaluated at 2I over n. Delta x. Now, this is the summation I equals 1 to n. F evaluated at 2I over n is 2I over n squared, because I'm plugging that into here, times, now remember my delta x is 2 over n. Alright, now this one is quite a bit simpler. So we still have summation I equal 1 to n, 2 times 2 is 4, 2 times 2 is 8 over n cubed, times I squared. But we can apply this. This is 8 over n squared. I squared is n plus 1, times 2n plus 1 all over 6. We multiply this out. We get 4/3 n squared times 2n cubed plus 3n squared plus n. So we get, once again, 8/3 plus 4 over n plus 4/3 n squared. Once again, you'll see if you take the limit as n goes to infinity, what happens to this? You see this reduces to 8/3. All right. So basically, write this down. Here's your definition. All right, if f is continuous and non-negative on the closed interval, a to b, the limit as n approaches infinity of both the upper and lower limits exists, and they're equal to each other. And we are going to use delta x as b minus a over n, and f little m is your minimum value on the subinterval, and f big M is your maximum value on the subinterval. And we're just going to use S sub n as our limit. Now, when you're done, put this in your notebook. When you're done, turn off the video, finish your homework.